So now we move away from series and into strictly parallel RLC circuits. In this section, we'll study the impedance and phase angles of parallel RLC circuits, also conductance, susceptance, and admittance now in the parallel RLC circuit. So we're going to see the value of using those inverse relationships, conductance versus what we learned about resistance, susceptance and admittance, what we learned about reactances. Okay, so we'll move forward with the parallel schemes and then eventually we'll get back to our resonance. So if we look at this simple RLC parallel network, one resistor, one inductor, one capacitor, we can see that the total impedance now can be calculated using those reciprocal values that we learned before as the sum of the reciprocals method, just as we did for resistors in parallel. So we see here that 1 over the impedance then is equal to 1 over the resistance, 1 over the inductive reactance, and 1 over the capacitive reactance. Okay, and then if we want to invert that and get back to our impedance now instead of our admittance, then we take the inverse of that. So 1 over each one of those. So we've seen this before in our DC studies. So the best way to handle this, let's do an example. So we want to find the impedance in polar form for the parallel RLC circuit. So we've got one resistor at 100 ohms. We've got one inductor reactive at 100 ohms and one capacitor reactive at 50 ohms. So if we start off with the relationship, our inverse relationship, the sum of the reciprocals, then 1 over the impedance then is equal to, as we've seen before, 1 over the resistance, 1 over the inductance, 1 over the capacitive reactance. So enter your values and this sets you up then for our next calculations. So if we apply the rule for division of polar values, then it's just a matter, as we've seen before, we move the value in the denominator into the numerator, change the sign on the angle. Okay, so 1 over 100 then for the resistance then becomes 10 millisiemens at an angle of 0. 1 over 100 for the inductive reactance, 10 at an angle now of minus 90 degrees in millisiemens. And then for the capacitor, 20, we invert 50, we get 20 millisiemens at now a positive angle of 90. So that recall that the sign of the denominator angle changes then when it's dividing. So it's just a simple invert it, change the sign. Recall that the sign of the denominator then changes. Next, convert each term in its rectangular to its rectangular equivalent and combine. So now we have 1 over the impedance equal to minus 10 millisiemens minus J 10 millisiemens plus J 20 millisiemens, and that brings us to then the vector relationship 10 millisiemens plus J 10 millisiemens. Okay, so phasorially or vectorially, then we have combined the like terms so that we have this as far as we can go. So now we take the reciprocal to obtain the impedance Z and convert it to the polar form. So 1 over that value that we just determined, then we have to then apply Pythagorean theorem and the inverse tangent for each of those values. So 10 millisiemens squared plus 20 plus 10 millisiemens squared, add them together, take the sum, do the take the square root, and then the inverse tangent of 10 over 10. So we have the inverse tangent of 1 essentially. And so we have 1 over 14.14 at an angle of 45 degrees in millisiemens. Invert that then one more time. Now we're back to ohms. 20.7 at an angle now of minus 45 degrees in ohms. So the negative angle shows that the circuit is in fact capacitive. This may surprise you because X sub L is greater than X sub C. However, in a parallel circuit, the smaller quantity has the greater effect on the total current because its current is the greatest. Similar to the case of the resistances in parallel, the smaller reactance draws more current and has the greater effect on the total impedance. So in the circuit then, the total current leads the total voltage by a phase angle of 45 degrees. So this here we're just restating what we saw before in terms of conductance, susceptance, and admittance. The concepts of conductance, capacitive susceptance, and inductive susceptance, V sub C and B sub L, and finally the admittance, which is our inverse for our total impedance, were discussed. Okay, so again, you should be familiar with these. Write these down in your notebook. Keep track of them because we're going to be using these inverse relationships, conductance, susceptance, and admittance throughout the rest of this section. As you know, each of these has a quantity then of Siemens. So typically in millisiemens, but instead of ohms, it's in Siemens. So another example. For the RLC circuit shown, determine the conductance, capacitive susceptance, inductive susceptance, and the total admittance. And then the last step, determine the total impedance. So the first thing we're going to do is we're going to calculate each of those from the values given: the conductance, the capacitive, the inverse capacitance, the inverse inductance, and the total for our admittance. So 1 over R is equal to 1 over 10 at an angle of 0 because it's purely resistive, gives us 100 microsiemens at an angle of 0 degrees. We do the same thing with the capacitive reactance. Capacitive reactance value then 10 at an angle of minus 90 for a capacitor, k ohms. The inverse on that gives us 100 at an angle of positive 90 degrees in microsiemens. For the inductor, 1 over X sub L, then at an angle of positive 90 degrees. So insert our values, 5K, 90 degrees, K ohms. We end up with 200 at an angle of minus 90 degrees in microsiemens. So now that we have these three values calculated, we can put them into the vector relationship, Y total. The admittance is G plus J B sub C minus J B sub L gives us 100 microsiemens, and then the other two terms are the imaginary terms, J 100 microsiemens and minus J 200 microsiemens. So from the total admittance then we can determine the total impedance. So the total impedance then is equal to 1 over the total admittance, which we having converted here to 141.4 at an angle of minus 45 degrees using the Pythagorean theorem and the inverse tangent. So 141.4 inverted gives us 0.707. Moving the angle minus 45 degrees into the numerator gives us a positive 45, and now we are in K ohms. So that was our conversion then, using conductance, susceptance, and admittance to calculate, and then doing the inverse to gain the impedance value. So as you've learned, the smaller the resistance in a parallel circuit will dominate because it results in a larger branch. Recall the capacitive reactance varies inversely with frequency, and that inductive reactance varies directly with frequency. That's just the math. We've seen that before. In a parallel RLC circuit at low frequencies, the inductive reactance is less than the capacitive reactance. Therefore, the circuit is considered to be inductive. As the frequency increases, X sub L increases, X sub C decreases until a value is reached where X sub L is equal to X sub C. That's our parallel resonance. As the frequency is increased further, X sub C becomes smaller than X sub L, and then the circuit becomes more capacitive. So we can see then in our simple illustration here what's going on when we look at the current as it flows between the resistor branch and the capacitor in the inductor branch. So we can see there, in the display here, small current, then I sub C L, I sub C, and I sub L, apart from each other. So the current here has decreased significantly based upon a larger current through the individual current branches for the capacitor and the inductor. If we look at the waveforms, we can see the waveforms then, in each case, I sub L, I sub C, and then the total for the two in the parallel branch, I sub C, maximum, I sub L, maximum, 90 degrees or 180 degrees out of phase with each other. The combination of the two then tracks as it being more inductive or more capacitive, but the magnitude, the amplitude is considerably less. So I sub L and I sub C effectively subtract from each other's. If we look at the phasor relationships, then we can see that 180 degree or 90 degrees minus, 90 degrees plus relationship as it relates to the current through the resistor. So this is your typical current phasor diagram for a parallel RLC circuit. The total current then can be expressed then, again, we go right back to our form for the Pythagorean theorem and the inverse tangent, where the ratio of the total for the current to the total resistance. I sub CL is the difference in I sub C and I sub L and the total current into L and C branches. So we can look at another example here. We'll go ahead and tackle this when we come back.